we are glad to see Ananya, and till now we switch our language to English, and I hope in a month Ananya learn Russian, and then we switch again to Russian. So, unfortunately, today Ivan Vladimirovich is a little bit sick, so we start with the talk due to Ekaterina. Please introduce your title yourself.
That M be algebraic variety with monoid structure. It means that they have a multiplication from M times M to M, which is associative and admits a neutral element.
So what are the assumptions from the ground truth?
Algebraically closed. Yes, of arbitrary characteristic. Okay. Let G be the group of invertible elements. It is well known that G is algebraic group, which is open in M as algebraic variety.
So do you assume M to be irreducible?
Yeah, today M be normal, irreducible. And well-known theory.
So in this case, open means also dense.
Yes.
So this is just a problem.
Okay. So theorem from algebraic group theory, if they have G is quasi-affine algebraic group, it appears that G is affine algebraic group. In the same way, it works for algebraic monoids.
So you claim that this is a known result, right? So
Yes.
this is a known result.
Yes, it is known result.
So which is about algebraic groups.
Yes. So, and in the same way, it works for algebraic monoid. So, if we have algebraic monoid M, which is quasi-affine as algebraic variety, it appears that M is affine. So from the first theorem, we can see if they have affine algebraic monoid. It follows that the group of invertible elements G is also affine. Because if M is affine and G is open in M, it appears that G is quasi-affine algebraic group, and by this theorem we have that G is affine.
Are there any references for these theorems?
For this this fact is well known, and this one is from Renner. Okay, so as I just said that if M is affine, it is easy to see that G is also affine. But the opposite statement is not very easy to prove. So if we have normal derivative, so our main aim for today is to show if we have normal irreducible algebraic monoid with affine group of invertible elements, it follows that our algebraic monoid M is affine group.
Am I right that if M is affine, G is affine, this follows that G is main principal open subset, yes?
I'm not sure about it.
Okay.
Why?
Oh, it seems that
So apparently this is not obvious.
it is not obvious.
even true.
A principal open subset is affine again, and
But if we have an affine open subset, it doesn't.
it's not always principal. I don't know examples, okay.
Me.
To prove this theorem, I need some preparation, and I will start with definitions.
Oh, this is the goal.
Yes. Definition 1. If we have
So in fact, this is a generalization of the theory there,
Hmm?
right? This is a generalization of this.
no, the second theorem
Ah,
we
sorry. I see.
will need to do in the proof.
Sorry.
It's just an illustration for the previous theorem. That, for algebraic monoids, it works in the same way. Definition. So if we have G times G variety M, such that there exists point X in M with open orbit of X or X. And isomorphic to our group G. Then M holds G embedding.
No, to G but to G times G by
Where G is morphic to G times G by diagonal set. So then M holds G embedding.
So what is OX in this the orbit?
Yeah, it is the orbit of element X by this action. So then M called G embedding. This G embedding called symbol G embedding. If there exists only one closed orbit.
I'm a little confused over this. One closed orbit means only one orbit which is closed, or a closed orbit which can be different from OX.
No, OX is not closed. you have only one orbit which is closed.
Yes.
Oh, there may be other orbits which are not closed.
Okay.
Okay. So it's not transitive.
And now M is not a monoid, just
Yeah, the
a G.
definition for every G times G variety.
But there is a projection between, for example, affine monoids and G times and G embeddings.
Actually, you can equip this M with the monoid structure.
If M is affine
Is M is
and
affine.
affine monoid, then it has a structure of G embedding.
Okay.
As an illustration, we have the following theorem. Rittatore. 98. That we have, if we have M is an algebraic monoid, it follows that M is simple G embedded. The G is the group of invertible elements.
Sorry, since we are thinking about whether the varieties are fine, then it's very vital. Here M is affine or not?
No.
For
Here M
any.
is arbitrary. It works for normal irreducible, maybe for
We do not assume M to be affine.
No,
It is-
M affine. And M again is normal irreducible algebraic variety. So sometimes this unique closed orbit is called Tema of our algebraic monoid. So before starting the proof, I need one more theorem. It's Sumithero theorem. So let G be a affine algebraic group. M normal is irreducible. G variety. And YB closed orbit. Then there exists open U, which is subset in M such that U is G invariant. Contains our orbit Y, and there exists such finite dimensional G model such that there exists G equivalent open submatrix of our open subset U into projective space P with.
It's an open subspace.
Hmm?
It's
So
an
open
subspace.
environment means that
Locally closed.
it is isomorphism with the image, and it is closed in the closure of the image. Or so it's open in the closure of the image.
So I would say that U is embedded into a as an open subset into a closed subvariety of P of V.
Yes.
But here you state that it is open in the whole of P of V.
So here denote the closure of image by X, which is projected variety in P at V.
So this looks better.
Okay, so today we'll
So
not prove this
probably-
theorem, I just will use it for my next.
Will you use it in this form?
Yes.
Okay, so you will use finite dimension G modules in this construction.
I will use it that we will have an embedding into projected variety.
So I would say that usually this theorem is stated just as M can be covered by open G stable for the projective subvarieties.
In the paper that we discussed on my previous talk, it was stated in this form.
Yeah, yeah. So this is just another form, but probably it's more difficult for comprehension.
This is just the same because we don't use V. Just V is says that X is projective, nothing more, because we do not use V at all.
We don't use V, we just use this three-dimensional projective space.
Okay, no problem. Sure.
Okay.
I wanted to say that this statement looks rather technical.
Yes.
And I'm trying to say that this theorem can be stated in a more transparent form, in my opinion.
Okay, but we will use it in this form.
Okay.
Okay. So firstly we will use this theorem to prove that if M is algebraic monoid with a finite group of invertible elements, then M is quasi-projective variety. So by this theorem, we have that M is simple G embedding. And they denote the correspondence closed orbit by Y. So to prove this statement, I will use symmetry theorem. So I recall that if M is algebraic monoid, then M is simple G embedding. It means that there exists only one closed orbit, and we denote this orbit by Y.
I'm sorry, I'm confused. We will not going to prove this theorem by Ekaterina Presnova.
So I will not prove this and these theorems. I will use it just for proof that this result.
Okay.
So today we will try to prove if we have algebraic monoid with affine group of invertible elements, then our algebraic monoid is also affine. So by Sumahira theorem, there exists an open G invariant open subset U, which contains our closed orbit. Since U is G invariant, it is union of some orbits.
So this U is quasi-projective by Sumahira's theorem.
Yes.
Wait a minute.
So, since U is G invariant, it follows that minus u is also G-invariant. Moreover, m minus u does not contain any closed orbit.
Contradiction.
So it is easy to see that the closure of every orbit is a union of orbits having smaller dimension. So the orbit of the smallest dimension contained in m minus u is closed. But here there are no closed orbits. So this set is empty. It means that m is equal to u, and it means that we have embedding from our algebraic monoid m to some projective variety x. Okay. So I will fix this result here. And we will use it later. So for the next step of proof, I recall a few definitions about line bundles maybe from previous talk. So if they have a morphism of algebraic varieties which is mapped from L to M, such that the image of every point is isomorphic to one-dimensional vector space, the M is equal to union of such subsets UI, where which are called trivializing open subsets in M, such that the preimage of UI is isomorphic to UI times A. And the following diagram is commutative. Moreover, we have a set of functions Fij from this expression Ui and Uj to T star such that Fij times Fjk is equal to Fij. So here we have our variety M and L the line bundle. So the next definition from the previous talk is G linearization of line bundle. So if we have a line bundle and we have an algebraic group G which acts on our algebraic variety M, so the linearization is an action of our group G on algebraic variety L, such that firstly, if is G equivariant, and secondly, for every G in G, for every point X in M, the action of element G on fibers is a linear map between vector spaces. So if you have such action, we say that this action is a linearization of lemma. And finally, I will define zero section. So it's the map from M to L, such for every trivializing open subset U. The restriction of this UI. Okay. So the restriction of this map on open subset UI given by the formula
So UI again, plus.
Roma has changed U to UI, so you can.
Thank you. Okay. So it is easy exercise to prove that this map is well defined.
So this is a morphism.
So I define it
well
only
defined,
on open subsets UI.
Intersections.
Yes, and
That's fine. We can continue.
okay. And I will denote by L star the line by bundle L minus zero section.
So probably you should say that this zero section is also G invariant. Right?
Mm.
It's obvious.
Because this is.
Because U is one of the trivializing subsets.
And because this thing is linear.
Yeah. So because this map is linear. So zero is taken to zero.
But maybe it's better to write in one line because it is difficult to understand.
For a minute.
Fine. This is also a Algebraic, right? So this L star is with the
Yes, it's just-
connection of G.
Yes. Exactly. G again the affine algebraic group. M be normal algebraic variety, which is G embedding. And P is such line bundle which is G times G linearized. Then we can consider the following diagram. This is embedding denoted by I. Here is pullback of our line model. And we will denote this part of diagram by H.
In fact, this is just a restriction of this line bundle to know the subset.
Yes.
The star in the sense of the middle.
First we will restrict our line model and then we
First a pullback and then
add
No,
star.
So the
Oh, yeah.
inner star means actually a restriction.
I'm sorry, what does it mean? I star.
Pullback.
Formally, this is
Fullback of
pullback.
what? I don't see any.
Of this line model.
This bottom is I, yes. I'm
Yes.
sorry.
But we discussed that I is an embedding, so the arrow above is also the embedding. Just a restriction.
Okay.
So then H is isomorphic to G times T star, and H star is H embedded.
So H is. So do you mean that H is an algebraic group?
Yes, it's a product of two algebraic
So
groups.
is it obvious that this variety is naturally equipped with the structure of an algebraic group?
What is the question?
From this diagram, is it obvious?
But for me, no.
This is the assertion of the lemma.
So one of the assertions.
So now I will try to prove it. Okay. So they have G times G linearized line bundle. So G acts on fiber corresponding to unit element, and this fiber is isomorphic to one-dimensional vector space, which is isomorphic to our fluid K. So this action is by diagonal set G in G times G.
So this.
Given by GL is equal to GG L.
So G is considered as diagonally inverted into G times G.
Yes. So here they has G times G linearization. And now we have action of group G.
So this G preserves the point 1, and so it acts on the fiber.
Yes. Because this action is linear, and L1 by this action goes to LG1G inverse, which is again equal to 1. Okay,
This was a comment.
okay, so this map is a linear map between one-dimensional vector spaces. So it just multiplication by some character of group G.
So actually this pullback is G times G linearized line bundle on the homogeneous space, right? And it is given by a character of G, as we know. This is a comment, so you can ignore it.
Okay. So moreover, we have that element A, G, A, G inverse acts on element L. The L is is in I think -1 G. Just by multiplying the character lambda in L. So let's prove it.
So what is it? It's on the left.
On the left. So we have G times G action on L.
On the
So A and GA, G inverse
is from G.
is element of A from G.
Some special type of elements in G and G.
So so to prove it, we consider the composition of elements 1 G inverse, AA, and 1 G on element L.
So, what is L? L is an element from the fiber
Over G.
over G.
Of element G.
And when we apply these two elements, we go to another fiber. Am I right?
Yes. So
G
So
times
firstly,
G.
we act by element 1G.
Maybe we need to say that what is the G times G action on G? It is left-right multiplication.
No. My question is, okay, let's proceed.
So
just
A
I'll ask later.
is from the fiber of element G. So we start with LG.
Okay.
So then it goes to the fiber 1G, G inverse.
Because of left-right multiplication
Because
action.
the action is left and right multiplication.
Okay.
So
This is another fiber.
yes, it is L1.
I don't don't understand this equality. We apply to
I
A.
try to explain it.
Okay.
So this diagonal element acts now on L1. And by this element, that goes from L1 to LG again. So we started with element L. Yes? Goes to something L dash. So here we know that G acts on this fiber just by multiplying with lambda.
Okay, you mean that you go through the
So
same
here they
path,
have
yes?
L8, L dash. Lambda L, L dash.
Katya, you mixed G minus 1 and G in the line you're trying to prove.
Upper.
Yes. G minus 1 and 1.
This is. Yes, thank you. The third action is inverse for the last action is inverse for the first. So
now it's
L dash goes to L, and now we have lambda L.
Yes, now it's
Or lambda L,
yes.
L.
I missed this too.
Okay. So the next step is to change our linearization. So means we will change the action of G times G on algebraic variety L. For this, firstly, we'll extend our character group G to the character of G times G. Now it is a character of group G times G. So now I can change my linearization. So now element AB.
So we extend this character to the bigger group G
To
times
the
G.
bigger group.
Just not depending on the second argument.
The star is the new linearization. So the element AB acts on L is equal to L tilde.
So you introduce a new linearization on the same one minor.
Yes.
And this is done by multiplication by a character.
So I will explain it a little bit later. So L. So this one, since lambda tilde is equal to lambda G, so we have this one is equal to lambda A, lambda A, AB. Here is the previous section.
And minus inverse.
Yes. So here the when we act on the fibers, we multiply it by some character. And here we divide by this
So do you
character.
want to trivialize this?
Yes. So, now, the next idea is that L is trivial over G. We have a statement from previous talk that there are no non-trivial G linearizations over G. Since it is linearized line bundle, we have that it is trivial.
And do you understand right that we have done it trivial by hand? This is by just by multiplying this factor, and this is you say that this is common.
So since it's trivial, they have that E star L is isomorphic to G times K. It appears that H, which is equal E star L star, is isomorphic to G times K star.
As a variety.
Yes.
As an algebraic.
So we have this isomorphism as algebraic varieties, and now we can equip this variety with the structure of an algebraic.
I think, yes, it's true. Moreover, we can consider H times H action on A. Star. By GS G dash T is equal to ST inverse G dash star A. So by the construction, it is not really difficult to check that the restriction of this action on H coincides with multiplication in H as an algebraic group. It follows from, so here we multiply by character, and when we change our linearization, we divide by this character. So it is not difficult to check that the restriction of the action coincides with multiplication in H. Moreover, H is open subset in L. So G is open in M. Then I star L is open in L. And H is open in I star L.
It is an open orbit of this action.
Moreover, it is open orbit.
And the stabilizer of the point is H diagonal is bent.
Yes. And so, as a result, H is coincides with open orbit of this action. So by definition we have that L star is H embedded. How much time I have? Whoa. Lemma 2, proved by Denote and Fujita. Let F be normal projective algebraic variety. So spoiler, this x and x from our lemma is the same algebraic variety.
Keep this in mind.
So L be ample invertible shift. So LP from N to X be line bundle associated to. So today I will not define ample invertible shift. I just want to say that there exists the correspondence between shifts and line bundles, and I will think about it as about good line bundle. And continue to work with line bundles. So it's just something then lemma 2 works. Then there exists such algebraic variety Z, such that Z is normal and affine. And secondly, N star is equal, which is equal to N minus 0 section, is isomorphic to Z minus single point. So as a result, N star is quasi-affine. So I will use this lemma to prove the following theorem. Theorem 2. If M normal irreducible algebraic monoid, with a fine group of invertible elements, then there exists G times G linearized line bundle such that firstly L star is a affine algebraic monoid. Secondly, P from L star to M is a morphism of algebraic monoids. And finally, M is isomorphic to geometric factor of L star by K star, A star. So it is easy to see that if we will prove theorem 2, it will be enough to prove theorem 1. Because if we have a geometric factor of geometric quotient of affine algebraic variety by reductive group, and
So it is the same as a categorical quotient.
yes,
And that's why it is affine.
yes, and result will be affine.
Maybe try something.
Hmm?
Try something.
I will prove it here. So M is isomorphic to quotient of affine algebraic variety by reductive group. Since it is well known that M is also affine. Okay, I have 30 minutes to prove theorem 2.
So I mean this is difficult.
Yes.
Not very difficult, but more difficult than this.
So we have already proved that M is an open embedding into projective variety X. So we can extend our diagram. So, and let's end the line model.
But there is no L yet.
Yes, so consider our
So we are going-
projective algebraic variety X. So, and let M be line bottom as in lemma 2. We just put line bottom, then lemma 2 works. Now we can define L as a pullback of this line bundle and have this big diagram. Moreover, we can.
But so again, L will be just the restriction of N to N, which is an open subset.
Yes.
Yes. So L is open in N, and from lemma we have where H is open in N.
But we don't yet have G times G linearization in there, right?
Good question. So lemma again from previous talk. For every line bundle L on N on X, such that group G acts on variety X, there exists N such that this line bundle is G linearized.
So we replace N by this 10 to the power.
Yes, we start with some line bundle, then applies this lemma, and
Can G times G linearized on
and now we have G times G linearized. So we apply this lemma to G times G action on it. Okay. Firstly, I define two maps, mu1 and mu2. Mu1 maps from H times N star to N star and given by formula H1A. The next map is from N star times H to N star and given by formula one H inverse.
H is big.
So do you want to prove that we can equip N star with the structure of an algebraic node?
So yes, we have that L star is H embedding. So and we have multiplication on H, and we extend this multiplication.
We try to extend it.
And now we try to extend this multiplication on the whole L star. So here we can see that mu1 and mu2 restricted on H times H coincides with multiplication in H. So since they coincides on intersection, so since H times H is equal to intersection of H times N star with N star times H, and mu1 is equal to mu2 on this intersection, they can extend both of them to the whole to subset U, which is equal to H to the union of these two parts, to the H times N star union with N star times H. So it is easy to see that you have codimension in n star times n star greater or equal to 2. So we have mu. It's a map from u to n star. So we extend mu1 and mu2, which coincides with multiplication in h to from u to n star. So, and this map is good defined, is regular on subset with codimension equal or greater than 2. So, since it works with normal algebraic varieties, we can extend mu to the whole variety z, which we have from lemma 2.
To n star.
N star, n star, to n star. So to finish the proof of this theorem, it is enough to show that mu n star times n star is the subset of n star. So since n star is h embedded, we have multiplication in h. So since we construct mu as
You explain why it is enough to prove this thing, yes?
yes.
With what?
Why if we prove this
So now
then
that
we will prove everything.
So now we have a multiplication from n star times n star to our affine algebraic variety from lemma 2.
Then star differs from that by only 1 point, right?
Yes.
Yes. So the previous mu was 2 n star. But n star is not affine, it is quasi-affine. So when we do something like closure, we go to z.
Yes. So actually we have so mu is a map from n star times n star to n star, right? And
To
we
the
can
closure of n star.
We don't know really why to n star.
To the closure of n star and by
Nice,
lemma 2
yes,
because
yes, yes.
n star is z minus point
But the closure of n star is z.
is z.
I see.
Yes, is z from lemma 2.
I have a question.
Okay.
Maybe a codimension of the complement of U is not less empty because
Yes,
because U is open and
Yes, of course.
Yes. U is open? Yes.
Complementary and not U.
Or U.
because U is open and stuff.
You mentioned codimension.
Not you,
Codimension of the complement.
Not you,
not
okay.
you, but n star minus
Okay,
u.
sorry. And star.
Yes.
Yes. Sorry.
And star times and star minus U.
Yes. It is
And star times and star minus U.
Sorry.
Greater or equal to so why it's enough to prove it?
So, first I would show if we will prove it, it's enough to prove our theorem. So, since H is open in L, and H is an algebraic group, we have an associative multiplication on L star.
Because it was associative on an open subset.
Because H is open subset in L star, mu coincides with multiplication in H, and multiplication in H is associative and admits an equal element. Secondly, L star is open subset in L star by the construction. And N star is quasi-affine. So as a result, L star is quasi-affine.
And then we apply this theorem here.
So as a result, L star is quasi-affine algebraic monoid.
What's the next step?
Yes. So and by the construction, they have that P is a morphism of algebraic monoids.
No, you have already to say that since it is quasi-affine, then by the theorem of Renner it is affine. And this is what we are going to.
Yes. So,
So star is affine.
so then L star is quasi-affine, and the theorem from the beginning of the talk, it appears that L star is affine algebraic monoid. And by the construction, they have that P is a morphism of algebraic monoid, because we had G times G linearized than 1. And finally, since no everything about fibers, and in this article he used one more lemma to prove that this one is a geometric quotient of algebraic varieties. So I have a few minutes to prove that mu L star times L star is a subset of L star.
So we have still 15 minutes.
Thank you. Okay. Let me have two elements U V in L star. And we want to prove that mu TV is again in L star. First, there exists trivializing open subset in M. Such that PV, PU is in U. So, since they have a map from A star to M, this is multiplication in algebraic monoid M. This is again an element of M, and M covered by trivializing subset.
So you choose any open subset which the
Containing
product
is
is contained there.
And let M be the multiplication on M. It's the usual multiplication on our algebraic monoid. Let W be the gray image of U. And subset in M times M. W dash will be equal to E minus 1 tilde W intersect with H times L union with L star H. So since P is mapped from L star to M, E tilde is a map from L star times L star to M times M.
It's P times P.
It's P times P. So the first idea is that W dash is open in this part of intersection. So U is open. The image of open subset is again open. And it appears that W dash is open as well.
At the intersection of two open subsets.
The main thing is that this big bracket is open, this H times L
The
star.
H, so H is open and star. So this part is also open. So we intersect two open subsets in L star. Moreover, P minus 1 tilde order, or W minus W dash has codimension greater or equal to 2. they again have a situation so it appears that mu W dash is a subset in P minus 1. One minute of what y2.
So if you multiply elements in W dash, then the W dash is projection to V.
Yes.
Or to U. And when we multiply elements and W is the preimage of U in the multiplication. Yes, the multiplication M.
Oh, okay. So W is image here,
M is the multiplication, and we try to check that
and W dash is in image of lies in image of W.
the multiplication M and U, they are affine.
So okay. Okay, but
So if you will multiply elements in W dash, they lie over some elements in W. And when we multiply elements in W, we obtain U, element in U.
yes.
So above here we obtain element in P in the preimage of U.
So W is here is an image of U. So if we have two elements in line bundle, in H star times H star. So then when we multiply each to the other, we goes to U. On the other hand, if we firstly multiply it, since we have G equivariant line bundle, so P since P is G equivariant, they again goes to U. It means that in line bundles it goes in one bundle it goes to P minus 1 U.
So you use the fact that the diagram is commutative.
Yes. Sorry, it's too late. Yes, and since here we have codimension greater or equal to 2, they can extend our loop to the
To W dash.
W dash. So by
Oh, no, not to W dash, to the inverse of.
so since we had that restriction of nu mu dash to W dash. Can be extended to mu tilde from P minus 1 tilde W to the P minus 1
minus 1.
minus 1. So the idea is the same with the proof of lemma free when we talk about topology.
And they are all normal by lemma 2.
And they are normal by lemma 2. So, and it is easy to see that mu tilde coincides with mu on intersection, which is open. And it appears that mu is equal to mu tilde. And as a result, since U and V, the pair U and V lies in W by the construction, we have that mu V is in P minus 1 U.
Another side of D.
Oh, sorry. Yes, and we know that U is trivializing open subset. So the preimage of U is isomorphic to U times E star. And it is subset in L star by the construction. So as a result, mu L star times L star is a subset in L star. So, and this, by the statement we can finish the proof of theorem. I think that's all for today.
Okay, thank you, speaker, a lot. And do we have some questions? And so, when I asked this already, but I don't remember the answer. If you have some other group of invertible elements, I don't know, elliptic curve, then you have not any interesting monoids with this group of invertible elements, just only the same group. Am I right?
It's for complete varieties, group of invertible elements is the same varieties.
Okay, and if you have a mixed group, some, for example, direct product of affine and complete, then the monoid is in somehow also a direct product, or I don't know. Can we learn all the monoid by learning algebraic groups and affine algebraic monoids? Or this is much more complicated question to study all the monoids?
Certainly it should be written something about this in Bjorn's article, but I can't follow the answer.
Okay.
So I would say that if it were true, then it would be known.
Known for whom? Not for me at all. But maybe my question is, of course, not to prove this fact, but whether it's known.
There was something like this, but I don't remember this formulation.
And one more question is about, okay, do you have an example of affine monoid with, of course, affine group of invertible elements, which is not a principal subset. Is it possible? What I asked at the beginning.
So one should think.
Do you know some facts about this, how this open subset embedded, maybe some known facts about this embedding?
So what do you mean by principal subset?
Probably
Just
this could follow from the general fact that all affine algebraic monoids can be realized as submonoids of the matrix monoid. So in this case, the set of invertible elements will be just determinative in zero.
Oh. Principally means that the complement is a hypersurface. Okay, maybe some more questions. Then we finish. Thank you very much. So, who knows? We proceed in 1 week. And what talk do we have next week?
You mean next?
Next week.
Talk about questions.